Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in chapter 5 of this playlist that I'm calling Comparing Population Means. And we're in part 3 of a little mini series that I'm calling Manova, which is Multivariate Analysis Variance. In part 1, we gave some background and intuition and introduction to Manova. Part 2, we introduced 4 test statistics. And in part 3 here, we're going to do an example. So the data that we're going to use is from an FTP site given here, and the data is T62 root, and it's an experiment conducted in from 1918 to 1934 on apple trees of different root stocks. Now, a root stock is the actual root system of the tree. So essentially, all commercial fruit trees the top of the tree is different from the root system, and that root system is called the rootstock. But they put like an apple tree on a rootstock that's like resistant to disease, produces juicier apples, and that's actually all commercial fruit trees are like that. And actually, this is one of the beauties of being a statistician, is that you learn so much about so many different areas. So this experiment, we have 8 trees from each of 6 rootstocks. And the variables that we're going to collect from each tree, there's 4 of them, so it makes it a multivariate analysis. Trunk girth at 4 years, extension growth at 4 years, trunk girth at 15 years, and the weight of tree above the ground at 15 years. And what we want to test are the mean vectors for the 6 different root stocks. Are they the same, or is it at least 2 different? And from previous videos, we calculated H, which is a hypothesis matrix, which is essentially the between covariance between the different populations. E is the error matrix, that's sort of the within covariance structure. And then E plus H is something that we'll need in one of the test statistics. The 4 eigenvalues of inverse of E times H are these 4 eigenvalues, which it turns out these are the only 4 values that we need for the 4 different tests. But if we look at Wilks lambda, which is the generalized variance of E divided by the generalized variance of E plus H, which ends up being the product of these eigenvalues like this, is 15.4, and it's less than the rejection region, which I don't have here because I don't have a table that has that exact value, but I know that we reject. So we reject H naught, and we conclude that the rootstocks are the mean vectors for each rootstock is different. Now, Pillai's trace, and that's my best guess of how to pronounce that. My apologies if it's not correct. It's the trace of the inverse of E plus H times H, which ends up being the sum of these eigenvalues here, which is 1.3, which is greater than the corresponding rejection region for Pillai's test, and so we reject. Lawley-Hotelin's test statistic is the trace of E, the inverse of E times H, which ends up being the sum of these eigenvalues. That's 2.9, and when you transform it by the degrees of freedom associated with E and the degrees of freedom associated with H, it becomes 24.539, which is greater than its respective cutoff value. So we reject. Now, Roy's largest root test, we just take the largest value, which was 1.876, and then divide it by 1 plus that same value, and we get 0.652, and it's also greater than its cutoff value, so we reject. Now, a big note here is because we reject H naught, and we conclude that at least 2 mean vectors are different. Now we want to know, of the 4 variables, which ones are contributing to us rejecting the null hypothesis. And to do that, you conduct univariate one-way ANOVAs to investigate which variables contribute to the rejection of H naught. And the big note is you only do univariate analysis after you've rejected the multivariate analysis. That's a big note here. Now let's just jump right into R, and we read in the table, the data using read table, and it doesn't have a header, which means it doesn't label the variables. So I give it names so we can, use them later. Rootstock. Well, if we look at the head of the file, which means print the first 6 rows, rootstock is the numbers 1 through 6, depending upon what rootstock system they were using, and then these are the 4 variables that were measured. Here there's 6 groups. P is 4, it's the number of variables, and there's 8 observations per group, so that's N. Now let's look at the mean vectors by group, and that's what MVBG stands for. And essentially we just calculate the column means for a given rootstock, and then we store it in this vector, or this matrix, MVBG. Now if we print it, notice that each row is a mean vector for that sample, so for a specific rootstock. So it's 1, 2, 3, 4, 5, 6. So this is the average of 8 observations, right, for that given rootstock. So those are the means. Now to compute H, which is the between variance or between covariance of these mean vectors, you just take its covariance, times this. So we don't actually want the covariance, but we want that sum of squared distances from the grand mean. That's what this is. And the covariance divides by how many groups there are, and there are 6 groups. And so you have to divide by, or multiply it times k minus 1 to get rid of that, and then take it times n. That's our H. And this is it, and it agrees with what we have in the example above. Now you can take a more traditional route where you take the means minus the grand mean, and then take the vector product of these two times n, and you get the same matrix. And so this is actually kind of closer to the formulas, but the first way was so much easier. Now to compute E, we compute the within covariance for each rootstock system, and then we add them together, and that's what this is doing. So we calculate it for the first rootstock, and then we loop through 2 through k when k is 6, and we calculate the covariance structure and add it to the previous one, and then we just loop through it, and we get E, which is what we got in the previous, and then E plus H, you could just add them and it prints it. Now we need the eigenvalues of the inverse of the error matrix times H. And this is it. So you solve E as the inverse matrix times H, and eigen is the function that creates eigenvectors and eigenvalues. We only want the values, and this is it. So Wilks lambda is the determinant of E divided by the determinant of E plus H. Or you could just take the product of these lambdas like this, 1 divided by 1 plus lambda. Pillai's trace is the sum of these lambdas, which is 1.3, or you could take the trace of the inverse of E plus H times H, and you get the same thing. Lally-Hotelling is the sum of the lambdas, which is 2.9. The Roy's largest root is you just take the largest eigenvalue and calculate it this way, and it's 0.65. And those are the values. And then you'd have to compare these against a book or somewhere they have the tabled values, and then compare whether to reject them or not. But we're going to use R. And to do that, it's a Manova statement, and you have 4 variables in the dependent variable, and rootstock is the independent variable. and you store that function into fit. And now you just call the summary of fit, which actually is a wrapper function to summary.manova, I'm pretty sure. But you say summary fit, but we want the test to be Wilks, and it produces a Wilks value and a p-value. So this is what we use. So the p-value is less than 0.05, so we reject. But now one big note is the way they calculate Wilks. Over the years, they've found different ways to calculate it, maybe more efficiently, and or they end up being a function that's very similar to the original, and so it's a little bit different. And the Manova in R says it does the calculation 100% like SAS computes its values. So this value is actually a little bit different than the way it was originally computed, in which we just went through. But we're not going to go through that, but know that it's a slight transformation, and then an approximate F test that's derived, and then a p-value. And this is what we use in practice. And then to look at the Roy's largest root test, or we get a p-value of, it's actually the same value, so we reject. Pilates test, a little bit different, same p-value, we reject. Summary fit test Hotel and Lawley, it is the same p-value, so we reject. Now, since we've rejected HO, since HO is rejected, now we want a summary of all the univariate ANOVA models to see which of the 4 variables are contributing that. And the way you do that is summary.AOV. So that's the summary of all univariate AOVs from this model fit. And then it pumps them out. So response 1, if you know that between the different root systems or root stocks, it's significant. So the response 1 is different depending upon which root stock system we're in. Now response 2 is actually, the mean is different between the root stocks. The p-value is 0.001. Now looking at response 3, the p-value is 0.18, so it's not enough evidence to reject the null hypothesis. So we say that the mean response for 3 is similar between the root stocks. Y4 is p-value is 0.13, so we don't reject, and we say it's similar between the different root stocks. So variables 1 and 2 are the variables that contributed to us rejecting the null hypothesis. Okay, so I'm out of time. I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.